In this video lesson, I'd like to dig a little deeper into the way in which electromagnetic waves can be propagated through space, and maybe focus a little bit on an example involving radio waves. I want to start by reminding you of something known as resonance. And resonance, as you probably remember, is just a phenomenon in which there's a large response in amplitude when a system is driven at its natural frequency. So you've probably had a physics professor in the past show you this demonstration using two tuning forks. The key to this demonstration is that each of these two tuning forks is identical in terms of the frequency it sounds at when struck. So the first tuning fork creates a driving frequency, and all we mean by that is it's the one that sends vibrations out through the air. Now the second tuning fork, the slight variations in air pressure associated with this sound wave cause the second tuning fork to vibrate, and if the frequency of the driving source and the frequency of the second ones are matched, then there's a large response in amplitude, so much so that if you strike the first tuning fork, you can, after striking it, pinch it with your fingers and totally stop it from vibrating. The second one will continue ringing for a long time. And I'll provide a video link of this demonstration in case you've never seen it before. If you put a little clamp on the second tuning fork, then it still has a frequency it rings at, but it produces a different pitch than the first one, so they're no longer tuned to one another and sending out a driving frequency that's different than the natural frequency of the second tuning fork doesn't produce this resonance response. So I bring this up because there's an electronic analogy to this same type of behavior. You can create a resonance condition using light waves, and in particular, the radio part of the spectrum. I'll probably provide another video link that shows you how you can build a crystal radio. If you have a cardboard tube and you wind it and you keep track of the number of windings you make, then you can control the inductance of a coil. Call it a solenoid or an inductor. And then wired along with this in parallel is a capacitor. So here's a close-up view of the type of capacitor you could use, a variable capacitor. So the knob on this variable capacitor is just turning a shaft. Now part of the variable capacitor is a stator, which is just a bunch of metal plates that are stationary. And then the rotor is attached to the shaft that you turn, and if you turn it as far as you can in the counterclockwise direction, then the surface area of the metal plates in the stator and those of the rotor don't face each other, and the capacitance then approaches zero. If you instead turn it in a clockwise direction, then all the metal plates face each other, and you're just essentially making a variable parallel plate capacitor, and the capacitance goes up as you turn the knob to the right. So with a fixed inductance and a variable capacitance, you can control the frequency of this circuit, and hopefully you recall that the frequency for an LC circuit, that oscillating electric circuit, is 1 over the square root of the product of the inductance and the capacitance. So the trick to this demonstration goes something like this. You take two of these, and just like the two tuning forks that can resonate with one another, these two electric circuits can resonate with one another. So we'll say this one is circuit number 1, and the other one is circuit number 2. So one of them makes a broadcast, and the other one makes a receiver. On the broadcast circuit, you connect a battery, maybe a 9-volt battery. The other end, you strip a little insulation off of the fixed wires, and then the wire coming off the positive terminal of the battery can make a contact point. You can either touch it to this stripped piece of metal or pull it away, and so you can open and close the circuit, and when the circuit is closed, then there's going to be some magnetic field lines in the inductor, and also by closing the circuit you can put charge on the plates of the capacitor, so you have both an electric field, a magnetic field in the inductor, and an electric field in the capacitor. As you open the circuit back up and release the contact point, the electric field fades away and the magnetic field fades away. So the dropping out of the electric field creates some rate of change of electric flux, and the collapse of the magnetic field creates some rate of change of magnetic flux. So if we look at Faraday's law, the integral of E dot ds is equal to negative d phi magnetic dt, and the full version of Ampere's law says the integral of B dot ds is equal to, in the absence of conduction current, where all you have is displacement current, then the integral of B dot ds is equal to mu naught times epsilon naught times the rate of change of electric flux. So you don't just send magnetic field lines from the primary circuit or the broadcast circuit to the second one. You're actually sending varying electric and magnetic fields. They travel as electromagnetic radiation from one circuit to the next. But the second circuit has an inductor with the exact same value inductance, and if you tune both the capacitors so they have the same value of capacitance, then this would be a case where the driving frequency in the source of the electromagnetic radiation sent from the broadcast circuit matches the natural frequency of the second circuit, and even a low intensity radio wave can produce a significant response in the second current. So you use the second current instead of putting a battery on it. The second current has a light bulb. So we can see the source of the power is in the battery of the first circuit, but you can carry the energy from that circuit on a radio wave, and that radio wave produces a resonant response in the second circuit, and by rapidly connecting and disconnecting or tapping the wire from the battery onto the one part of the circuit where you've stripped away the insulation, you produce a flickering response in this light bulb, so you can send energy on a radio wave. So in our next video, we'll take an even deeper look at this and see if we can figure out the speed at which radio waves are broadcast through space.